We're going to start with chapter 5 today. It's sequences, mathematical induction, and recursion. Start out with sequences. Imagine that a person decides to count his ancestors. He has 2 parents, 4 grandparents, 8 great-grandparents, and so forth. These numbers can be written in rows as shown here. To express the pattern of the numbers, suppose that each is labeled by an integer given its position in the row. 1, 2, 3, 4, so on and so forth. The number of ancestors in the second row. The number corresponding to the position 1 is 2, which equals 2 to the first. Number corresponding to 2, position 2 is 4, which is 2 to the second power. For the rest of the positions, the numbers equal the 2 to the power of that position. For a general value of k, let a sub k be the number of ancestors in the kth generation back. The pattern of computed values strongly suggests the following for each k. A sub k equals 2 to the k. A sequence is a function whose domain is either all the integers between 2 given integers, or all the integers greater than or equal to a given integer. We typically represent a sequence as a set of elements written in a row. The sequence be denoted a sub m plus 1, a sub m plus 2, so on until a sub n. Each individual element, a sub k, is called a term. The k in the a sub k is called the subscript or index. M, which may be any integer, is the subscript of the initial term, and n, which must be an integer that is greater than or equal to m, is the subscript of the final term. The notation here indicates an infinite sequence. An explicit formula or general formula for a sequence is a rule that shows how the values of a sub k depend on k. So, define sequences A sub 1, 2, and 3, and B sub 2, 3, and 4 by the following formulas. A sub k equals k over k plus 1, and B sub I is I minus 1 over I. Compute the first 5 terms of both sequences. Well, be 1 over 2, then 2 over 3, and so forth. Here it would be 1 over 2, 2 over 3, 3 over 4, and so on. So it would appear that the sequence defines the same, both sequences define the same set of numbers. As you can see, the first terms of both sequences are those fractions, and it can be shown that all terms of both sequences are identical. Compute the first 6 terms of the sequence C, defined as follows. C sub j equals minus 1 to the power of j for every integer j greater than or equal to 0. Now, j sub 0 would be 1. J sub 1 would be negative 1. J sub 2, 1. J sub 3, Negative 1. Yeah, it would be alternating between 1 and negative 1. Even powers of negative 1 equal 1, and odd powers of negative 1 equal negative 1. It follows that the sequence oscillates endlessly between 1 and negative 1. So find the explicit formula for a sequence with the following initial terms. 1 minus a quarter, 1/9, negative 1/16, 1/25, and negative 1/32, or 36th. Well, denote the general term of the sequence by a sub k, and suppose that the first term is a sub 1. Observe that the denominator of each term is a perfect square. So it could be written as 1 over 1 squared minus 1 over 2 squared, 1 over 3 squared, and so forth. Now note the denominator of each term equals the square of the subscript of that term. And the numerator equals plus or minus 1. Well, from the previous example, the numerator oscillates back and forth between plus 1 and negative 1. It is plus 1 when k is odd and minus 1 when k is even. To achieve this oscillation, insert a factor of minus 1 to the k plus 1 power, or minus 1 to the k minus 1 power, into the formula for a sub k. Consequently, an explicit formula that gives the correct first 6 terms would be a sub k equals minus 1 to the k plus 1 over k squared for every integer greater than or equal to 1. Note that making the first term a sub 0 instead of a sub 1 would have led to the alternative formula a sub k equals minus 1 to the k over k plus 1 squared. You should check that this formula also gives the correct first 6 terms. It is convenient to use a shorthand notation to write such terms. To write a shorthand notation for writing sums was introduced in 1772 by the French mathematician Joseph Louis Lagrange. Introduced the capital Greek letter sigma to denote the word sum or summation. Might have seen that in algebra, algebra 2, I think. Definition. If m and n are integers and m is less than or equal to n, the symbol sigma k equals m to n of a sub k is the sum of all the terms a sub m, a sub m plus 1, etc. to a sub n. We say that this is the expanded form of the sum. We call k the index of the summation, m the lower limit of the summation, and n the upper limit of the summation. So let this sequence equal these sequence terms equal these values. Compute a sub k, the summation of a sub k from 1 to 5. Yeah? It'd be negative 2 plus negative 1 plus 0 plus 1 plus 2, which would be 0. From 2 to 2, a sub k, the summation would be just the value of a sub 2, which is minus 1. So there you go. And the terms of a summation are expressed using an explicit formula. For instance, it is common to see summations such as summation of k squared from k equals 1 to 5, or this other this equation, or this formula that we saw earlier with the negative 1 to the I power. Compute as the summation of k squared from k equals 1 to 5. It'd be 1 plus 4 plus 9, 14, which 14 and then plus 16 is 30, plus 25 would be 55. We can do basic math in our head. Yeah, 55. When the upper limit of a summation is a variable, an ellipsis is used to write the summation in expanded form. So write the summation of this in its expanded form. Let's see here. Let me see if I can. Let's see here. It would be from 0 to n. So it'd be minus 1 over 1 plus 1 over 2 plus minus 1 over 3 plus ... Sound about right? All right, let's see if it, yeah, 1 plus 3, or 1 over 1 minus, I got the signs backwards. But yeah, it alternates between plus and minus because the numerator is minus 1 to the power of n. And the last term that I didn't put up there would be minus 1 to the n over n plus 1. Okay. Express the following using summation notation. Yeah. So a summation. No. All right, so it would be k equals 0, because you're going to be having n plus k to n, and it's going to be k plus 1, because the first term is 1, and k is starting at 0. So you would start with k plus 1 in the numerator. The denominator would be n plus k, because your n doesn't change, because that's given at the in the summation symbol, and you're adding plus 0 in the first term, plus 1 in the second term, plus 2 in the third term, so it would be plus k. Now let's see if I did that right. Plus O. Yeah, to 2n. So it would be, well, they use I instead of k, but yeah, I plus 1 plus I in the denominator. The general term for the summation can be expressed as I plus 1 plus n plus I for each integer from I from 0 to n. The top index n of the summation is a free variable, because it may be replaced by any integer greater than or equal to the bottom index, and each such replacement leads to a different summation. For any particular summation at the top index acts like a constant. Thus, when the top index also appears in the terms of the summation, its value does not change from term to term. By contrast, the index variable, the lower number in the summation symbol, is bound by the summation symbol. It must take every value from the bottom limit to the top limit in succession. Writing a summation in expanded form helps relate it to our previous experience of working with sums. But for small values of n, the expanded form may be misleading. What is the value of 2 to the 0 plus 2 to the 1 plus 2 to the 2, etc. for 2 to the n when n equals 0 and n equals 1 and n equals 2? Well, it'd be 1, 2, and 7, wouldn't it? Because you're summing? No, so yeah, it'd be 1, 3, n equals 0 would be 1, n to the 0 plus n to the 1 would be 3, and then 7 for n for 2 to the 0 plus 2 to the 1 plus 2 to the second, 1 plus 3 plus 4, or 1 plus 2 plus 4. So it would be, when you evaluate a summation like this for small values of n, you can avoid mistake by imagining it in a summation form, in summation notation. So when n equals 0, yeah, it equals 1, 3, and 7. Okay, so using summation sign and separating off a final term. Write 2 to the, as the summation of k equals 0 to n of 2 to the k plus 2 to the n plus 1. How would that be written as a summation? Go all the way back to Algebra 2. How would this be written as a single notation? Because this is one term. It's not. So what is the single summation of that? It would be the summation of k equals 0 to n plus 1 of 2 to the k. Because you're adding a 2 to the n plus 1 to it, so you raise your upper limit by 1. So by the same token, b, rewriting this as a, by separating off the final term, you can eliminate the plus 1 from the upper limit. So you can go summation I equals 1 to n equals the summation of 1 over I squared plus 1 over I, 1 over n plus 1 squared. Does that make sense? Kind of, sort of? You're taking off the n plus 1 term and putting it out here and leaving the summation with the basic term. All right. So it would be, like I said, 2 to the n plus 1 to, or 2 to the k from 0 to n plus 1, and summation of 1 over I squared from I equals 1 to n plus 1 over n plus 1 squared. In certain sums, each term is a difference of 2 quantities. When you write such terms in expanded forms, you sometimes see that all the terms cancel except the first and last terms, which can be handy. Some sums can be transformed so that the successive cancellation of terms collapses the final result like a telescope. For instance, observe that for every integer k greater than or equal to 1 over k minus 1 over k plus 1 equals k plus 1 minus k over k times k plus 1. So you can find you can use this identity to find a simple expression. This is equal to 1 over k times k plus 1. Use it to find a simple expression for this summation. When you expand it out, you notice that the minus 1/2 and the plus 1/2 cancel each other out. Minus 1/3, plus 1/3 cancel each other out. Minus 1 over n and plus 1 over n cancel out, leaving behind 1 over 1 minus 1 over n plus 1. So you can solve a summation, get rid of the summation symbol by expanding it out, canceling terms, leaving what's left in terms of n. Product notation. Notation for the product of a sequence of numbers is analogous to the notation for their sum. Greek capital letter pi denotes a product. For example, a sub k, the product the product of the sequence a sub k from k equals 1 to 5 equals a sub 1 times a sub 2 times a sub 3 times a sub 4 times a sub 5. Definition. If m and n are integers and m is less than or equal to n, the symbol here reads the product from k equals m to n of a sub k is the product of all the terms, and we can write the expanded form as so. Come on. You're not cooperating. You're magnifying instead of swiping. There we go. A recursive definition for the product notation is if m is any integer, then a sub k, the product from k equals m to m, a sub k equals a sub m. And the product of a sub k for k equals m to n is equal to the product of a sub k from m to n minus 1 times a sub n for every integer n greater than or equal or greater than m. So the products of, let's say, the product of k from k equals 1 to 5 would be 2 times 3, 6 times 4 is 24 times 5 is 120, right? Sound about right? 120? I'm doing my math right? Yeah, 120. Properties of summations and products. The following theorem states general properties of summations and products. If the sequences A and B are sequences of real numbers and C is any real number, then the following equations hold true for any integer n greater than or equal to m. The sum of two summations is equal to the summation of the two sequences added together, if the m and n are the same. the multiplying a sequence by a product or by a constant is equal to the summation of the sequence multiplied by the product. And the product of two products is the product of the two sequences, assuming m and n are the same. So let a sub k equals k plus 1 and b sub k equal k minus 1 for every integer k. Write each of the following expressions as a single summation or product. So let's see here. You got the summation k equals m to n. Now, to bring this, you'd bring this 2 into here to make it a sub k plus 2b sub k, right? That makes sense? Doing 2 steps at once there, combining the 2 summations. Now substitute k plus 1. So that's k to the n equals m to n. It'd be k plus 1 plus 2k minus 2. I'm sorry. I'm not. 2k minus 2. So you would have the sum would be 3k minus 1, the summation. Right? Does that seem right? Does that seem right? Or did I screw up somewhere? K from m to n. Did I screw up somewhere? Let's see what the answer says. Yeah, okay, yeah, it was, yeah, k from m to n, summation of 3k minus 1. So, and likewise, you can add, multiply things together and get k squared, the product of k squared minus 1 from m to n. Change of variable. Observe that these two sequences are defined the same with different variables. Therefore, the summations are the same. So, you can swap variables around if they are defined the same. The symbol used to represent an index of a summation is an example of a local variable, often called a dummy variable, because it can be replaced by any other symbol as long as the replacement is made in each location where it occurs. Outside of that context, both before and after, the symbol may have another meaning entirely. In the same way, a symbol used to represent a variable in a universally or existentially quantified statement can be replaced by any other symbol as long as the replacements are made consistently. The appearance of a summation can be altered by more complicated changes of variable as well. So, for example, j from 2 to 4, the summation of j minus 1 quantity squared is equal to the previously defined summation of k squared from 1 to 3. So you can manipulate things to simplify expressions. Transform the following summation by making the specified change of variable. Change the variable from k to j, where j is k plus 1. So you would change the range. So you'd j equals 1 to 7, because it's k plus 1, so you have plus 1 here and plus 1 here, plus 1 here and plus 1 here to give you 1 and 7. And then then you would substitute k plus 1 into j, so you just have 1 over j. Simplifies the expression by changing the range on the summation. I think it, oh, you would do that. These screens can be difficult sometimes. Come on. In the 40s, I think. Notation. Change a variable. Here we go. So j, the summation of 1 over j from j equals 1 to 7 is the guess. Yes, the new subrange goes from 1 to 7. So you add the 1 from the definition of j equals k plus 1. And then you substitute the j in here. In this example, they solve for k and then substitute k for that value, but I just did it directly. So you obtain the summation of 1 over j from 1 to 7. J equals 1 to 7. Rewrite the summation here so that the lower limit becomes 0 and the upper limit becomes n. But the index of the summation remains k. First, transform the summation by you making the change of variable to j equals k minus 1. Second, transform the summation obtained in part A by changing all the j's to k's. The index variable k is bound by the summation symbol to take each of the values from 1 to n plus 1 in succession. When k equals 1, then j equals 0. When k equals n plus 1, then j equals n. So the new lower limit is 0 and the upper limit is n. Now n is a constant with respect to the terms of the sum. Unlike k, its value does not change from one term to the next. So, and since j equals k minus 1 and k equals j plus 1, you can write the sum as the equation as j over 1 or j plus 1 over n plus j plus 1. So the general term for the new summation is j is that j plus 1 over n plus j plus 1. And you can make it add that to the summation. And then change all the j's to k's in the right-hand side of the equation. Gives you k, the summation of from k equals 0 to n, k plus 1 over n plus k plus 1. Factorial and n choose R. The product of all consecutive integers up to a given integer occurs so often in mathematics that it is given a special notation, the factorial notation. N factorial is defined to be the product of all integers from 1 to n. So n exclamation mark equals n times n minus 1 times n minus 2, etc. to 3 times 2 times 1. 0 factorial is defined to be 1. So 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, and so on and so forth. You can see those numbers climb very quickly as the argument increases slowly. A recursive definition for factorial is the following. Given any non-negative integer n factorial equals 1 if n equals 0, n equals n times n minus 1 factorial if n is greater than or equal to 1. So the next example illustrates the usefulness of the recursive definition for making computations. 8 factorial divided by 7 factorial. Well, 8 factorial is 8 times 7 factorial over 7 factorial. That cancels, so it equals 8. Right? 8 factorial divided by 7 factorial. You expand out the 8 factorial, cancel out the 7 factorial, and you get 8. 5 factorial is 5 times 4 times 3 factorial over 2 times 3 factorial, 2 factorial, sorry. And that cancels that out. which leaves you with 20 divided by 2 is 10. Or you could have it 2 and this, 2 and cancel the 2 out of the 4, and that leaves 2 and leaves 5 times 2 equals 10. So you can cancel out a lot of terms, simplifying things. So in D here, you have n plus 1, times n factorial over n factorial. Cancel out the n factorials, and you're left with n plus 1. Right? So there you go. Come on. You're going to do this to me again? Oh, I don't like these slides. Come on. Where we go, factorial, and we'll just go to you have the 8 and 10 that we showed there, and then what was it, D? We were left with n plus 1. So you can cancel out things and simplify expressions when using factorial. An important use of the factorial notation is in the calculation of quantities called n choose r that occur in many branches of mathematics, and especially those connected with the study of counting techniques and probability. Let n and r be integers, with r being less than or equal to n, but greater than or equal to 0. N choose r with this notation is represents the number of subsets of size r that can be chosen from a set with n elements. So computing n choose r is n factorial over r factorial times n minus 1, or n minus r factorial. Because n choose r is always an integer, you can be sure that all the factors in the denominator of the formula will be canceled out by factors in the numerator. Many calculators have keys for computing n choose r. May have seen these buttons on a calculator or a scientific calculator. Do you have these on your calculator? No, the n choose r. Yes. Yeah, it's pretty common. The letter C is used because the quantities are also called combinations. Sometimes they're referred to as binomial coefficients because of the connection with the binomial theorem. So use the formula for calculating and choose R to evaluate the following expressions. Well, is it, I'm not going to write on the board and have it mess up again. This it shows you how to expand out the factorials and cancel out the factors and get your final results. The fact of 0 factorial is 1 makes the formula computable in some instances. Sequences in computer programming. I'm sure you've all been introduced to arrays in computer science 1 or 2. If not in data structures, if you've gotten that far. The one-dimensional array is very commonly used. The array is denoted by the elements of an array are usually denoted with square brackets holding the subscripts. Some languages I've encountered use parentheses to denote subscripts rather than square brackets, but it's the same meaning. The index variable for a for next loop is a local or dummy variable. The following 3 algorithm segments all produce the same output. For I is equal to 1 to n, print a sub I. For j equals 0 to n minus 1, print a sub j plus 1. For k equals 2 to n plus 1, print a sub k minus 1. They all produce the same output. Keep in mind, most programming languages start array indices at 0 rather than 1. Something to keep in mind. Application. Algorithm to convert from base 10 to base 2 using repeated division by 2. A systematic algorithm to convert any non-negative integer to binary notation uses repeated division by 2. Suppose a is a non-negative integer. Divide a by 2 using the quotient remainder theorem to obtain a quotient and a remainder. If the quotient is non-zero, then divide by 2 again to obtain a quotient q1 and remainder r1. Continue this process until a quotient of 0 is obtained. At each stage, the remainder must be less than the divisor, which is 2. Thus, each remainder is always either a 0 or 1. So, doing that for a equals 0 or 38 yields these quotients and these remainders, and you read up from the bottom. The results of these divisions can be written as a sequence of equations used in the format of the quotient remainder theorem. And then by repeated substitution, You get this down here. Note that each coefficient of the power of 2 on the right-hand side is one of the remainders obtained in the repeated division of 38 by 2. This is true for the leftmost one as well, because 1 equals 0 times 2 plus 1. Thus, 38 equals 100110 in binary. In general, if a non-negative integer integer a is repeatedly divided by 2 until a quotient of 0 is obtained and the remainders are found to be r0, r1, etc. to rk, then by the quotient remainder theorem, each ri equals 0 or 1, and by repeated substitution from the theorem, thus the binary notation can be read as r sub k minus 1, etc. to r sub 2 to r sub 1, r sub 0. I'm not going to go through this with a 29, but 29, the remainder is 1, 0, 1, 1, 1. So the representation of the number is 11101. And this is the algorithm that if you so choose to copy it and look it over and program it into a computer, these two slides here give the algorithm for creating a string, well, a sequence of integers, which you can use to generate a string that would be the binary representation of a decimal number. So, and that is about it for today. Quite a big slide deck for section 1 of chapter 5. Subsequent slide decks will be smaller. But anyway, have a good day. See you on Thursday.